Okay, so we have one more part that we want to take a look at, and that is a factor of s by itself, be it an s or a 1 over s. So we'd like to be able to do the Bode plots of either s's or 1 over s. We're going to look at 1 over s, and the reality is to look at s, you would just take whatever plot we have and flip it over the horizontal axis, and you get the result. Okay, so the magnitude. Okay, if you have 1 over s, you let s equal I omega, and the magnitude is 1 over omega. Just that simple. If it were an s on top, if this were just an s, you would have an amplitude would be omega instead of 1 over omega. Okay? The phase. All right? So 1 over s, that's really 1 plus 0i, so that's 0 degrees on top, and 0 plus omega I, so that's 0 minus 90. It's minus 90 everywhere. If you had an s on the top instead of 1 over s, it would be plus 90. Okay? So if you plot this, what does that look like? Well, you notice if omega equals 1, you'd get a 1. So you go through 1 radian per second. That's really simple. And you basically drop at 20 dB per decade. All right? Why is that? If omega equals 10, you have 1/10, which would be minus 20 dB. If it's omega is 100 radians per second, it'd be 0.01 minus 40 dB. And you're just dropping off. And this looks like this is, yeah, there we go, minus 40 dB at 100. Okay, so we have, this is just dropping at 20 dB per decade everywhere. There's no, it doesn't start at 0 and then make its way down. If you have an s by itself, everywhere and always, 1 over s is losing 20 dB per decade of frequency. If you flip it and have an s, it would just be flip across the 0 dB line. It's going up at 20 decibels per decade everywhere, and it goes through 1 radian per second. The phase is really simple to plot. If you have 1 over s, it's minus 90 everywhere. If you had the s, it's plus 90 everywhere. Now this, of course, then, what if you had, instead of 1 over s, you had 1 over s squared? What would that be? Well, if omega equals 1, it would still be 1. So you'd go through 1 radian per second, but instead of dropping at 20 dB per decade, you'd be dropping at 40 dB per decade. Okay? For every factor of 10, you drop 100. All right? If you had s squared on top, instead of going up at 20 dB per decade, you'd just go through 1, but then you'd go, the slope through that would be at 40 decibels per decade. Okay? Notice we have decibels on the horizontal, and we have frequency as a factor of 10. I said that wrong. Decibels on the vertical, and then we have a logarithmic scale on the horizontal, and that makes these kind of nice because that makes these lines nice and straight. Okay, so here's a slope, plus, if we had s squared, it would be plus 40 dB per decade. So increase by a factor of 10 in frequency. If you had s squared, excuse me, if you had s squared, you wouldn't have 90, you would have plus 180. If you had 1 over s squared, you would have minus 180. And that's how these things simply work. So for every power of s, you have a 20 dB per decade shift. The thing is, when you have s's by themselves, it's for all frequencies. For every power of s, you have a 90-degree phase shift. Doesn't matter what the frequency is. So boom. And if you have 2 of them, it becomes 180, 3 of them, 270, so on and so forth. So what do we have so far? We have, given any transfer function, it can be factored into the following components. A gain, s's, and this could be s to the n's. 1 over s, or 1 over s to the n's. Likewise, we have s on a plus 1, that would be a 0. This is a pole. We could have multiples of these, so to powers. And then we have complex zeros and complex poles, of which we could have multitudes. Everything can be factored into these parts without exception. So what we can then do is plot these parts individually, and then when we are done, we can just add them up because everything on a Bode plot, by taking it with log scale and decibels and all, everything just adds graphically. We will do one of these here in just a moment.